everybody. Hi, everybody. Welcome to the 6th GBM of Drexel AI. It is May 5th, 2021. We'll be talking about some stuff people did in the past week, but I want to talk about the fact that I have to write these expense reports, basically breaking down what we think we're going to spend in the next year with our funding. And I wanted to talk to a couple of people about this because I know it'd be cool when we're back in person in 2021 to talk, to bring in pizza, and I know we still want to do the shirts thing this year, the sweatshirts. So, hey Jeff. And I don't think Yit can join us tonight, but I kind of wanted to talk to a couple people about what we think for expenses next year, which isn't so exciting, but it's just what we got to do. I'll end up figuring it out. Maybe we'll get some pizza in next year. And I know we want to do that sweatshirt order. And we were talking with one company, Yit and I were talking with one company, and they're asking for 28 per sweatshirt, which isn't a terrible deal, but I know it was originally going to be like 23-ish. And then we were going to mark it up to 30 for fundraising. The company is called, I don't even know if it's a company. It's here, I'll just share my screen. It'd be this kind of style hoodie, but we have Drexel AI on it, and it's this plus the shipping to the location. So that's kind of why it ended up being a little more than we expected it to be. Yeah, I think their minimum order is 20, but we'll figure it out. Hey, Adam.
Hey, Ethan.
Hey. Okay, so we have some people here. So fast forward a year, right? I have to fill out an expense report, and maybe I don't know, the consensus would be what, pizza and sweatshirts. That's kind of what we're spending our money on. If you have any other ideas, let me know. I don't know what kind of expenses we'd get for the conference next year if we want to do it in person. That's something also to think about. I know this doesn't involve everybody, but I'm just looking for suggestions. If no one has any, we can just skip that.
Well,
I mean,
think
we can have some. Oh, sorry. We can have some for conferences, like some that are just like out of town, maybe just for like travel costs, maybe if it's in person.
Okay. Maybe we don't necessarily have to worry about funding for the conference because maybe OUR will give us money or whatever. Maybe they'll help us out. So maybe we don't have to worry about that so much.
Yeah.
Adam, what were you gonna say?
Kind of what Alicia said. Oh, wait, I'm sorry. Is it Alicia or Alicia?
Alicia.
Okay. So like Alicia said, I think it would be nice if like we didn't have to worry about like filling out the reimbursement forms after we already paid the $80 for the conferences.
Yeah, I don't think there's any way around that. I know we're not really supposed to use funds for conferences. I think that they actually made that pretty explicit.
Oh, really?
Yeah. So there's no way around that. Be nice, but we gotta do the whole reimbursement system or whatever. Okay, cool. So I've been in correspondence with, his name is Daniel Schwartz. I think he's also in Sparse Labs with Ed, and he gave a presentation on this architecture I talked about last week. Where's my Slack? And he did me a favor, and he was able to look at the model that we have already started to design, right? And so he ran it, and it didn't do too well. You can see that the discriminator loss is still much lower than generators. And then he actually removed the convolution operation, which we thought would help, and then the loss converges for both of the models, which was interesting. And then I know he's busy now, but here's kind of like the loss in another way. I don't know if this is with the deep convolution though. I think he said he removed that, but at least for the results section of the paper, we're going to have a much better architecture, and his knowledge in these specific architectures are much better than mine and Osamu's. But Osamu was great in trying to put all this together for us, and I think he saved the weights, or at least the weights were saved, and he saved some of the, I think, okay, let's go in here. Let's see. This is the first time I'm looking at this. I've been pretty busy today. Oh. That's the model. That's the model. And looks like these are binary files. Maybe they're predicted from the generator. I don't know. But something I wanted to do is I wanted to take the time to kind of figure out how we're going to visualize this, because it's important that when we have these predictions from the generator, we're able to kind of validate by what they look like. So if you guys remember, the input to the discriminator and the output of the generator is this square, it's a rectangular prism, where we have where each cube represents like a 1 by 1 by 1 angstrom allocation of space, right? So you can imagine that we have a bunch of these, and in each of these we have information pertaining to at least what we think would be a singular atom. It's a bad corner piece. Let's try this again. Oh, but you get the gist, right? You have one right here, one right here. And in each of these, so we have one in the middle, there is information pertaining to that atom. So we have a couple things. We have the occupancy. That's a dirty color. I don't like that. Let's go back. There we go. Occupancy, we have, and then we have one hot encoded labels. The first one is the atom type, so oxygen, carbon, or hydrogen, along with maybe sulfur. And then this one's the positional. Hey, Samu. And this one's the positional atom type. So there's a couple things we can do, right? We can look at the occupancy values, and we can, of the predicted structure, and we can basically put dots in a three-dimensional space, points in three-dimensional space where they're located. And depending on because remember, this is a continuous value. From 0 to 1, we can assign them maybe different, maybe we can like shade, maybe we can adjust the occupancy, like the occupancy, sorry, it's getting confusing. We can adjust the transparency, like the alpha of that dot when we're visualizing in space. But I don't know if that would necessarily be a good idea, because the occupancy isn't like a certainty that it's there. It's more like how far off it is from the center of that cube. But then for like the atom type and the positional atom type, we can assign just colors So we can kind of see if there is, if it's able to predict, an alpha carbon backbone connecting all the atoms. That'd be really interesting, because there should be alpha carbons kind of tracing out the line of the protein if it's predicting correctly. That's just an idea.
I don't think we need to visualize the occupancy if it's going to be like a problem.
Yeah.
Like in the paper, at least, like we can just mention that we use it in the calculations.
Maybe, okay, that's a good point. Maybe we just show non-zero occupancy values and then color them based on type and position.
I have a question. Is there a way to make the structure three-dimensional, like an image or something?
You want to do two-dimensional?
Or like three-dimensional, like width, height, and channels or something like that. Because the only reason I say that is kind of like currently it's really hard to notice if the gain is learning or not unless you actually go into the values and just check it. So I was wondering if
He sent me. Did you see the thing, the post?
yeah.
So the loss of I think we both realize that the losses are both binary cross entropy, right?
Yeah.
Okay.
But
how is it calculated for the generator? It should be different than for the discriminator.
for the generator, let me check. I forgot.
I almost wish.
I think like the loss function is just like you're maximizing what the discriminator is trying to minimize.
Yeah, that's pretty much it. So
Okay.
basically the correct labels are all zeros and it's trying to make the discriminate, trying to generate samples where the discriminator. Oh, that's interesting. Maybe I'm getting a bit confused. Anyway.
Because whenever I do,
it's working.
You think it's working?
Yeah, because I copied it from the TensorFlow documentation.
So I was gonna say, yeah. So whenever I do like regular deep learning on when I've done the regular deep learning on this protein encoding, when I showed you on the whiteboard, I'd always just use for my loss, I'd use mean squared error, but I guess it's different because we can't control that. We can't apply that because of the fact that it's a minimization. So it's a min-max problem between the same loss of the discriminator and the generator.
I think like the mean squared error is used like sort of indirectly because you're thresholding the probability that something belongs to like fake or
yeah, you're right. I guess that makes sense. So if you don't think it's really
I think part of the issue with like the convolutional stuff might be that we're not training it enough to converge, like, because when you're training a convolutional neural network, you're training like two sets of things. You're training like your filters and your like the stuff that you're putting into the convolutional.
Yeah.
Like it's a two operation, so it's like twice the amount of stuff that you need to
learn,
calculate, kind of.
Yeah, that makes sense. So maybe it's just a better idea to just forego that. But if you don't think that we need to visualize it, then that's fine by me. Maybe showing that the losses converges enough to say that it's able to learn, that the discriminator is able to do the entire training process, identify real and fake, right? And we know that there isn't a classification bias because it generates 50% fake, 50% real each iteration. And then eventually the discriminator is able to dramatically increase its loss to a point at which it's below actually what at a point where it actually outperforms the discriminator, which is interesting.
But he said it's not learning anything. So I
He's
think
Yeah.
what happened is that it just predicted those zeros or something.
Yeah, I think like if the generator was getting better, then the discriminator would be getting worse.
Yeah. Okay.
Oh. Can you make a script that visualizes the generator output? I think that can be like a...
I was thinking that, and that's what we were talking about on the whiteboard.
That might be a good idea. Like comparing the generated stuff to like the original data that we're feeding into the discriminator. Like
because now that I think about it, again, loss doesn't mean anything except unless it explodes or not.
Okay. Yeah, I'll work on this.
Okay. And
it's just going to be because one thing that's kind of a mess, right, is that this is a 1 by 1 by 1 angstrom cube. So like our precision with where exactly these atoms are won't be amazing, because we can only get it down to the 1 angstrom distance, right? When you think about like a cube that's an angstrom in size, right? This is like an angstrom in size. The atom really can be anywhere in this cube. So I think for simplicity, it could be here, it could be here, it could be here. Simplicity, I'll just put them in the middle when I do the when I visualize in 3 dimensions. And I've done that before.
okay.
I think like we just need to focus on getting the GAN to like the generator needs to be getting better, and like we need to show that that's happening when the discriminator gets worse, because that's like
The whole idea.
Yeah, I mean, like the general idea isn't that like both of the losses have to converge. It's that like the generated data looks like basically indistinguishable from the training data we started with.
Yeah. What if we supplemented this encoding with a second encoding, where the second encoding is a contact map? So you would feed in this as features to the GAN, but then you'd also have that n by n matrix, which we know works, right? Because that's what the paper was about.
Which paper?
The one you originally sent us.
Oh, okay.
Yeah. And then we feed both of these things, my amazing drawings, we feed both of these things into the generator or the GAN as features. Right? Because here, the information you have in this representation right here, this gives you the relationship. This gives you the distance between atoms. This also gives you distance between atoms, but it also gives you atom type. And then it also tells you the occupancy, which is related to energy.
Is the architecture we're using right now feeding in like something other than random noise to the generator?
No, it's feeding in random noise.
Okay. So like we would have to, our random noise would have to generate both of these like representations then if this is what you want to do
Yeah.
in the generator. So like, I don't know whether you want to like,
Would that
we
be
can't
difficult?
really use two different generators for two different representations of the same.
Yeah, we
Thing.
can do like each one separately, honestly.
I think it would be better to like put them both together.
Yeah. Can't you just overlay it on as like another dimension?
Yeah, I think you could. But I don't know, like, if that's all we're doing, we'd have to show that the stuff that we're adding has some real utility. Otherwise, the stuff that we did, it doesn't really mean much, you know?
Yeah. Maybe it would have utility if, sorry, I'm eating nuts here. It would have utility if when we reconstruct, because the best way to reconstruct a protein is from the contact map, right? This gives you so much more precision compared to this because you only have an atom is restrained to kind of a one by one by one by angstrom cube, whereas
And then it is contact maps.
Sorry?
Yeah, we should definitely use these then if that's like the best way to do it.
Well, that's what the paper you sent us did.
Well, yeah, but like we could do something other than what they did. You
We
know,
can do
like,
it better.
there's no need to like reinvent the wheel if it's just not going to be like as good as what they did.
Yeah. Okay. So we can use these, but I'm saying that maybe if we use these to give us positional relationships, in addition to using this, or some way, it gives, basically we want to get some way of representing the atom type. Or maybe,
I mean, you could just add that as a feature into your in your matrix, right? Like,
yeah. So
Yeah.
Yeah.
But for now, we kind of eventually, I get your point. But for now, I think like just the contact map will be.
Yeah, if the contact map versus like the 3D representation that you were like, I'm not sure like what the idea is in terms of like what it's representing that the contact map isn't, I guess is what, because that's like, if we're adding this other representation, it needs to add something other than what we already have.
Yeah.
By the way, I might replace the current term with this because it looks way better.
What? What is this?
Oh, it's called TF-GAN, and it's just TensorFlow's library of GANs. So you don't need to make the GAN.
Okay, so here's an idea. Instead of using that protein encoding representation, we have the contact map as one feature, right? So this is just this is like the contact map. But then layered, we have the atom type, and then we have the positional atom type.
Okay. Like, is this okay? I guess.
Really, you'd only.
How are we linking like the position of these atoms to their type in this representation?
Basically, for the contact map, you have basically you only need the lower left or upper right matrix, but for the atom type and the positional atom type, you'll just do it along the diagonal.
On another like layer?
Yeah, like right here. So like for instance, this would be like an n by n by 3 for these three features.
Oh.
And so
that's way better than the current one.
It is. So for instance, the contact map would be like this, right? And then the atom type will be like this, where you just have values down the diagonal, and the positional atom type would also be like that.
You mind like sending people some documentation about the contact map if there is any? Because I'm still not really sure like exactly how it works.
Oh, a contact map is an n by n matrix of pairwise distances between all the atoms.
Okay.
So you might look at like your first atom is in the upper left-hand corner. It's a carbon atom. You ask, okay, so how far is it from all the other atoms in the protein structure? And you calculate that Euclidean distance. And you do that for all of the atoms.
Is n
And
the
it's
number
like-
of atoms?
Sorry?
Is n the number of atoms?
It is.
Does it is like, can you infer which atoms are bonded together just based on the distances?
Yeah, you can use closest distance. I've done that before.
Okay. And can you make a Python script that reconstructs the protein from the contact map?
Yes. Yeah, I've done that too.
Oh, okay.
You
And
use
then,
multi-dimensional scaling, and then you can use linear algebra to kind of align proteins. And I did that in my poster.
okay.
So, and then also something else. I think this is a lot better. This is a lot better. So then I didn't even think about it like this. So then you can do like occupancy as another domain, because that's still a relevant energy feature right here.
Mhm.
Right? So then this would be like a
n times 4.
Yeah.
So like the IDs for each different atom, how are we encoding that? Because shouldn't that be tied to like its occupancy and like type?
What do you mean IDs?
Well, like if we're the molecule or whatever we're dealing with has its structure is made up of all these different atoms, and then like the atom type is connected to a certain atom. So like if our contact map is just a collection of like distances,
Okay,
we
sorry.
have an ID like from like this is from atom A to atom B, and then we need to like have atom A have like type something, right?
Right. Okay. So here, let me talk about this. So, right, the contact map. You understand, like it's a lower left or upper right diagonal matrix.
Okay. Yeah.
Going to the first ordinal feature, which would be the atom type. What we would do is we would just put values down that diagonal corresponding to.
Oh, that's like okay, I understand. So like the length, like the size of the matrix is how many atoms there are.
Yeah.
Is that right?
4, 10, 11, and like you might have 1, 4, like one might equal carbon.
Yeah, I understand. Or we should just use like, yeah, maybe I don't know. It's kind of messy to use like integers like that.
Okay, then you know what we can do?
You can use like,
You can use one hot encoded. You can do one hot encoding, but backward.
And if we do one hot encoding, we're gonna increase the number of channels so much.
Yeah, it would be.
So
Well, right, the atom type. Maybe we only need atom type. Maybe we don't need positional atom type if we only use closest to reconstruct it. So then atom type, we have 5 atoms that we need to do. So this turns into 8, or yeah, something like that. 6.
how many, like what is n in the standard representation that we would use?
like 10.
No, because 10 is the amino acids, right? And any amino acid will have probably like 10 or so.
Wait, 100.
I
guess 100 is fine.
think it's fine, right? Because
Yeah, that's not that bad at all. Like
the problem with our last one is that it was 74 deep.
Yeah, and there were so many useless zeros, so
Yeah, it was
database
too
is
sparse.
like uselessly large.
This is less sparse.
Yeah.
Right. And then for like atom type, right, we're gonna have a
well, like the lower left or lower right is going to be like kind of sparse, right? Because there's not bonds between lots of atoms.
well, okay, here's the thing. Here's something I thought about, right? Oh, this would be interesting actually. So, right, the contact map, you'll have the lower left diagonal filled in. The occupancy can actually be calculated for nearby atoms because you use the radius and the distance. You use the radius of the atom against like the distance of nearest atoms. So the the occupancy doesn't necessarily need to be along the exact diagonal. It can actually be around like, it can be around nearby atoms like this. So there's more, we can store more information by kind of expanding it out this way. And maybe to make the atom type less sparse, we can encode the atoms that are closest to a given atom. So let me see if I can articulate this well. Where am I for this? Do you guys understand what I'm saying about the occupancy with this? Or not really?
Yeah, not really.
Okay. Give me a second. So what I'm suggesting is that this equation right here
do we really need to use like a a tensor for this? Can we just like append like all this to one matrix?
like a vector.
Yeah, like they're vectorized, like, oh, the types of all the atoms are in one vector, and the occupancies of them are in another vector, and then just like append that to the side of your matrix, your contact map. Because it'll be the same length, right? Because there's n, if there's n atoms, then it'll be an n length vector.
Yeah, but I mean,
We can try multiple ways to represent the data.
yeah, but I think it might be cool to have them in channels, right? Because then the data kind of corresponds to a given, like the channels kind of talk to each other for a given atom or atom relationship. But what I was saying, so like we were saying how normally the occupancy would only be down the diagonal, but
Right.
maybe if you evaluated this for nearby atoms, so like RA would be in reference to a farther away atom, but it still might yield a non-zero occupancy value. However, this will go quickly to 0 because of to the 12th power here.
Right.
Will it help in deconstructing the protein?
No, this stores energy information.
Why do we want to get energy?
Because it tells you, basically, I think the idea when I did this is because it gives you an idea of whether the atoms are too close or too far from each other.
Okay, and you can't get that from the contact map.
No, you can't, because it depends on the van der Waals radius of an atom.
Okay. But you can reconstruct the protein from only the contact map.
Yes.
Wait, so if you, let's say if you have the contact map and you deconstruct the protein. Oh, I guess like the energy is different between like proteins?
Yeah, depending on the atom type.
Okay.
What's the point in using these different atom types and occupancy if we can just reconstruct the molecule from
right,
contact map?
There's the contact map gives you like, oh man.
I know, like the contact map is a collection of distances between all the pairs of atoms, right?
This was only used a contact map, and I can't encode atom types in the contact map. That's the problem.
Oh, okay.
And I don't know whether these atoms are unusually close to each other or unusually far away. And to get away from to get away from needing to find like the combinatorial relationship between each atom type and distances between atom types. You can just separate them into atom type and occupancy. That's the idea. Otherwise, I would need to learn, okay, if this is any of like 5 choices, this atom has any of 5 choices, this atom has any of 5 choices, and then they're whether or not they're far away is a function of their distance, conditional on what atom types are right here and right here.
Okay. Then if you have the contact map and the atom types, can we reconstruct any protein, or do we still need the occupancy?
Okay. So you can, the problem there, you can reconstruct the protein with those 2 information, but the problem is that you don't know whether it's, you don't know whether the energy, you can't say anything about the energy or the stability of the protein, right?
Oh, okay. So basically, if we just reconstruct the protein using the atom position and the contact map, it can be on like any part of that curve that you
Yeah,
just
it
showed.
can be. Yeah.
Okay, but if we have the energy too, can we like know which part of the curve it's on?
Give me a second.
Wait, can you repeat that with some? Which part of it?
So if we have the atom position in the contact map, we can reconstruct the protein, but it can be on any part of the energy spectrum for like how deteriorated it is. I was wondering if you have the energy thing, if you are able to understand like what energy level it is. Yeah.
You can, because in comparing it to other proteins, basically when you compare it to other proteins that might have atoms that are, more disorganized, they'll visually have they'll visually have like different values. So in comparing structures, yes.
Okay. So basically for all those channels, it will help in reconstructing like the true structure of the protein.
Yeah. So you can kind of think the atom, the contact here, basically they add different levels of detail, and it's not always obvious. The contact map tells you where each atom is from each other, and that can reconstruct like the skeleton.
Yeah.
And then the atom type, would give you the identity of each of the atoms. And then on the 3rd level, the occupancy tells you whether those atom types, those specific atom types, are far or close to one another compared to other proteins. And all of those features are necessary. In my opinion, all of those features are necessary because, yeah.
I still don't. I don't think that doing like different channels like that is a.
Yeah.
It seems like a wasteful like representation, because you can encode the same amount of data in just a vector.
Okay. We can do just the vector.
Yeah.
So you can just try out both.
I mean,
because like the amount of like the size of your input is going to like be 3 times as large.
Yeah, you're right. Is there any, is there any way we could feed this first channel through like a 2D convolution and then the second ones through like 1D convolution in a network?
Why do you want to do that?
Because, it'd be cool to still retain the 2-dimensional space of this contact map right here.
Sure. Yeah. But like, what is your goal with like the convolution operation? Like what do you think you're trying to do?
Passing like 2 inputs.
Sorry?
Why not passing like 2 inputs? Like the first one, it's the contact map, and the other ones are just vectors.
Yeah, that's the idea. Because you'd be splitting it up, right? The contact map would be this 2D representation, but then the occupancy and atom type would be these vectors. So I'm gonna just.
I think that's possible, but like it sounds like overly complicated.
Okay, so then we don't.
Yeah, I'm wary of like adding like stuff like that. I don't know, like it just doesn't seem like it has a utility beyond being able to say that you did like convolution. Like,
Okay, you don't think it's necessary?
no, not really. I don't know.
Okay.
Like the benefits I think of convolution are more easily seen in like vision based stuff. I don't really see.
You're probably right.
Anyway, so I guess for now the priority is just making this structure. But honestly, I have no idea how to do it.
Oh, you mean doing this? That's not terrible at all.
Okay.
I'll just make NumPy files and send them over.
Okay, thank you. And also the visualization one. If you can do that, like the game doing the game and everything will be way more easier.
Do we want to do atom type and positional atom? Do we want to do atom type and positional atom type? Or I guess because we're representing in vector, it's easier.
What's the difference between positional and atom type?
Okay, atom type gives you like alpha. It gives you carbon, oxygen, hydrogen, sulfur, nitrogen. The positional atom type basically tells you where it's located relative to other atoms. So for instance, like we know that each amino acid at least has one alpha carbon. But then the beta carbon kind of goes down the R chain, the radical group. And then you have different carbons associated with what's inside of the radical group.
Is that positional atom type like something that's easy to encode?
It would be an ordinal vector. It would just be.
It's like, okay.
It would just be another n vector with basically another one hot encoded matrix. It would be a one hot encoded vector that's n the dimensions.
Okay, why not?
So for everyone following along at home, we just had a very big discussion, but I'll try to draw it out. So we have kind of 4 different features that we want to encode that all add information about the protein. This would be positional. It's not special. Right. So we have the contact map, and you can kind of think of this as basically a way of telling how far any given protein is from the rest of the proteins. And this has been used to reconstruct 3-dimensional figures, to 3-dimensional objects time and time again. The atom type, this would be an n by m matrix of one hot encoded vectors corresponding to different atoms. So for instance, if we had like 4 atoms, carbon, hydrogen, nitrogen, phosphorus, then m would be 4, and we'd have one hot encoded vectors corresponding to each of the n atoms in the structure. The occupancy would just be a n by 1 vector, where you have an occupancy value for all of the atoms, and then the positional atom type would be another one hot encoded matrix, an n by k, right, where k is a number of positional atom types.
Okay.
Yeah.
So that would be like, this would be like a 3n if we, or n by 3n or something. Or like total.
This is
like
n.
if we appended them to like on the right.
Okay.
And n by 2n plus k or
so let me think.
Something like that.
N squared plus nm plus n plus nk. That's what it would be.
Can you add kind of like constraints? For example, like I'm quite sure it's possible to make a kind of like a structure in the contact map, but that structure will be invalidating the other features. You know,
What
Is
do you
there like a situation like that? For
Um,
example, so I was thinking like if a generator generates an image which
Mhm.
is that size, I was wondering if it can be the case that the contact map will represent one protein and occupancy will represent another protein or
Well,
something
I,
like that.
I think the only way to do that would be to separate it. I think Osamu's asking the question, right? We have some noise that goes into some generator, and then the generator spits out this size vector. We want it to be the case that this we want it to be the case that this corresponds to the contact map, this corresponds to the atom type, this corresponds to the occupancy, and this corresponds to the positional atom type. I think the only way to do that is to split it up and to have it predict like 4 separate things.
I think like
I don't know if there's any other way to do that.
And
I
I
mean,
was
it's still representing like
Something in the feature space.
respective features. Even if we put them together, we can just like parse out the representation after it's learned.
oh yeah, I meant more like if it's possible that kind of given a contact map, for example, like given the first n squared, we can kind of like do some math operation on the others to make them the same protein.
What do you mean?
Also,
The same size? Is that what you mean?
I don't know, like for example, if the contact map has like says the contact map says how close something is, right?
Yeah.
So that has some relation. Does that have some relation with the occupancy?
Yeah, it does, but you also need the information about the atom type. And
Okay, so for example, it can be possible that given like a certain value in the contact map that it's impossible to have some value in the atom type and occupancy, right?
Yeah, so if you have, I guess that is true. Okay, so what I think he's saying is that if you have some contact map, you kind of want to, what would be the use of that?
Oh, I was thinking like it can quickly reject invalid structures from the generator.
Yeah, so one way,
Or we can, another utility might be that given the generator output, it can convert it to a valid protein.
I think we could like, just add some operation to our generator that combines features in that way. If you want, or like, like.
Yeah, but only if it's easy. Like if it's hard.
Oh, yeah,
like,
I mean, I think it would, if it reduces like redundancy in our representation, that might be good.
Yeah.
I'm trying to think, I don't think there is a way to do that.
Oh, okay, then never mind.
I don't think there is a heuristic. One heuristic might be that, if there's n atoms, you expect there to be n. There's n atoms. If there's like j amino acids, you expect there to be j carbon atoms. That's like one thing. Alpha carbons.
Mm-hmm. Okay.
Mm-hmm.
We can just train it and see how it goes.
Yeah, I like this a lot better.
Yeah. Oh, yeah. Like the one image approach is really good because then we can just use GAN libraries to do it.
Yeah. Okay. Okay, cool. Does anybody have any questions about literally anything? Because I think we just popped off.
I can help some more with the paper. Sorry, I've been kind of MIA.
No worries. I'm gonna have to. It might take me a while to actually. I don't know. I have the size of this data is gonna be a lot smaller, but I also have to work on. I was showing this earlier. I have to work on the expense report, which is where we figure out how much money we want to ask for next year. And I got to figure out the food and all of this stuff. Actually,
Oh, yeah, you need to continue the tradition of free pizza at Drexel AI.
Yeah, I would like to do that. I just don't know. Like I don't know how to do the finance stuff. But I'll have to figure that out.
Got a bag, you know.
Yeah.
No, it's just because like I want to talk to someone who's done this before. I think Yit has done this before, and I want to talk to him about it. So I got to figure that out.
Yeah.
Due in a week, so I have some time. I'll just
Alright.
keep it open on my desktop until I remember to do it. That's how things usually go anyway. Cool. I'm gonna try to do that tonight actually to generate that structure. It won't be too difficult because all I have to do is just tie some functions together and just write the output and just run it for a bunch of protein IDs that I already have. I'll run it for all 10,000 because the data will be a lot smaller. And right, we're already at 1,000 pages for this. Wow, we're already had
1,000 pages.
we already had 4 pages for this. So what'll have to change is the figure,
Yeah.
this, and then the conclusion, and then I think we'll have more robust results to talk about in the abstract. But we are limited to 4 pages here. So
All right. Yeah. Sounds good.
cool. Yeah. Oh,
We can talk about it over Slack.
here we go. So is anyone so for sweatshirts, right? Is anyone not interested in getting a sweatshirt? Speak up. It says Drexel AI on it. Okay.
Is this only happening next year, like after I graduate, or is this?
No, we're sending Yet got in contact with some kind of boot. I don't even know what to call it. A spring tee.
Okay. Yeah,
knockoff,
sure. Yeah. Whatever. Yeah.
and they're like bugging us to like buy from them now. They're like emailing us every day, like, how's your boarding? Hopefully, you don't see this video. And so we have to respond to them, but it'd be around like $28-$30 for a sweatshirt. I don't know.
Plus markup, right? You wanted to mark them up.
The markup would be from 28 to 30.
Oh, okay. Only $2.
We'd be getting $2 from it.
You have to it's a minimum order of 20, right?
Yeah, what I might do is I might just like buy a bunch, and I just might buy the minimum and then just like sell it to people when I'm here next year.
Yeah, we can have
And then
stock.
I'd have to take care of 30 sweatshirts. So that's something that I could do. Okay, cool. Awesome.
Sounds good.
Yep, so that's tonight. Conference is the end of May, so if you haven't submitted paper, do it.
Is this minimum abstract or paper?
Either extended abstract with a poster or a paper.
Okay.
So you can submit your thesis, right, Jeff?
Right. Yeah. Like, do I have to submit the entire paper, or can I just like submit part of it because I haven't finished it quite yet?
Submit part of it. Submit. I don't know. There is no page minimum.
All right.
We did that on purpose. And then
like half a page, you know.
Dan, Alicia, Mally, if you're interested in doing anything, I know I mentioned something to Alicia about putting something together on our previous work. I like to see everyone who come to the meetings like present, because that's like the people who are most engaged. So please.
Do you want to present about this stuff?
I think we'll have some people talk about it. I don't think I will, because I want to do something from like either last term, or I want to do my own work too.
Yeah, I understand.
So I don't want to present everything.
Okay, cool.
Cool. Yeah, if you have any questions, I'll stick around, but I guess that's it for me. I'll generate some data and send it over to you guys, and I'll let you know.
All right. Sounds good. Thanks for the meeting.
Yeah, you got it.
Yeah.
See you guys.
See ya.
Yeah. See ya.